Okay. What I want to talk about in this one is we're going to talk about solutions and concentration. We're going to get into this. One of our key things is we want to remember that solutions are homogeneous mixtures. And we hit on that in the beginning of the semester, but we want to keep on with that right now. Remember, the homogeneous mixture looks like a pure substance. So it has, um, what's the word I'm looking for? So it has a uniform composition, right? Everything looks the same. Okay. So when we're talking about solutions, um, we're thinking about that kind of stuff, right? We use the words like dissolve, things are dissolved in, and all that kind of fun stuff. So solutions are homogeneous mixtures. They could be any phase whatsoever. I've got three random pictures here to think about this. This is representing air. Air is a mixture of nitrogen, oxygen, carbon dioxide, a little bit of water, blah, 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 right? It's all gases, but the whole point is it's homogeneous. You can't see uh, what's going on in there. Down here we have salt water, right? And salt water is homogeneous mixture, right? Sodium chloride, magnesium chloride, a lot of water, some other stuff, dissolved gases and all that fun stuff. So also solution. Liquid, air's a gas, salt water's a liquid, brass is a solid. Brass is an alloy, which is a solid solution of copper and zinc mixed together. Okay. We want to get a couple of terms in us here too while we're thinking about it. One of those being solvent. The solvent is the substance that's present in a greater amount. You can think about that solvent is whatever the is doing the dissolving, right? It's the bulk of the solution. Okay. The solute is the thing that is dissolved, so it's present in a lesser amount. Okay. And we want to think of this as like the solute plus the solvent together make a solution. Okay. We're going to keep our Gen Chem focus on things that are aqueous. And remember, aqueous, we give the phase label AQ, and this means we're dissolved in water. Okay. So if we were to say we had sodium chloride, aqueous, that's sodium chloride that's dissolved in water. But we could also have sodium chloride that's a solid, and that would mean it's a solid. Okay. We got to pay attention to the phase labels when we do this. Okay. Why am I having issue? There we go. Okay. So concentration is a term we use to talk about the relative amounts of stuff in solution. So it's how much solute is in a particular amount of solution. Okay. There are lots of different ways to think about concentration. Here we're also talking about relative terms. We can think about things that are more concentrated, which means they have a higher concentration, or things that are dilute, which means they have a lower concentration. These are relative, so there's not always a specific numerical value of concentration that goes with these two things. Okay, you can think of one of the things that happens, like if you're in chemistry for a career or job or whatever, um, you'll buy stock solutions that are concentrated solutions of stuff. And that's just a term that we use um, to indicate that it's a stock solution. And that would just mean different things, right? Different numbers of concentration could be there. Um, and we'll talk about dilution in another video to talk about how uh, what it means to dilute the solution down and to have a lower concentration. So really we want to think about concentrated is just higher, and diluted just means lower concentration. Okay. Um, and there's a lot of different units we could use to express concentration. Um, we're going to stick to, for Gen Chem 1, we're going to stick to molarity. Okay. And molarity talks about moles of solute per liter of solution. And so we could express that as moles per liter. And molarity is always given this capital M unit. Okay. And this is going to be a little bit disturbing or hard to work with sometimes because we're going to see one unit, but it's really masquerading as two units, right? It's really two units pretending to be one unit. Okay. So when we're thinking through dimensional analysis and stuff later on, we want to make sure that we use this correctly. Okay. When we're making a solution, This person in the diagram here is making a solution of potassium permanganate. Okay. What they're doing is they're getting all their stuff together. They figured out how much they want. What do they do? They're trying to make 0.1 molar potassium permanganate. And so they figured out how many grams they need. Okay. They've weighed out the correct number of grams and they've added it to some water in what's called a volumetric flask. Okay. Um, and then they've dissolved it in the water, make sure it's completely dissolved, and then filled it to the line with distilled water. Okay, volumetric flask is great for making solutions because we don't care about how much water is in the solution, right? We only care about what the total volume of solution is. Okay, and here the flask gives us one very specific volume. I think this person is using, where'd it go? A 250 milliliter flask. Okay, um, so the flask is a specific amount of volume for the solution. And so don't have to measure the water. You just have to figure out what your solution is. Okay. Um, right. So let's look at some examples. How are we going to work with um, concentration? And just like we saw with density, there's two real main ways that we'll work with concentration. One of those is molarity is going to be the answer, right? The answer is concentration. So here we're going to have potassium dichromate, and we have a 500 milliliter volumetric flask. We want to know what is the concentration of this solution, okay? Um, so to tackle this, every time we have one of these where molarity is the answer, we have to do three things. We got to figure out moles, we got to figure out liters, and then we have to do moles divided by liters, okay? This will be our answer. Sometimes moles or liters are given to us. Sometimes we have to do a little bit of a calculation to figure that out. But every time concentration is the answer, we're going to do moles for, if we got to figure out moles, we got to figure out liters, and we got to do moles divided by liters to get our answer. Okay. All right. Let's tackle this dude. Let's figure out moles. All right. Moles. Okay. Gave us the molar mass. It's up here. My picture's over it. There we go. What do we got? 1, 2, 3, 4. 1, 2, 3, 4 grams. Since we're keeping it potassium dichromate the whole time, we'll just leave the formulas out. But if you're changing what the idea of the formula is, which we will be doing, you want to make sure you keep your formulas in there. Okay. Our molar mass is 294.20 grams. And this will give us moles of potassium dichromate, which for this one is 0.04194443 moles. I'm going to label this K2CR2O7. All right. Then we want to figure out liters. Where did I not? Oh, because my finger was writing, not my pen. Again, it happened. Liters. Fast forward for me being stupid. All right, liters. Oh, excuse me. So sorry. All right, liters. 500 milliliters. 1 liter is 1,000 milliliters. Remember, don't get those conversion factors backwards. Okay, so this is 0.5000 liters. Okay, this is liters of solution, which is what we need. Okay, because we want moles of solute, which is the potassium dichromate, and we want liters of solution, which is the solution, right? That's what we figured out. So that's what we have. Lastly, we got to figure out our concentration. So our molarity is going to be equal to our moles, 0.04194443 moles divided by our liters, 0.5000 liters, which is 0.0838885 molar. What do we want? 4 significant figures, because both this and this are 4 significant figures. So we'll round this to 4. 0.08389 molar. And here, if you feel like it, we can say this is potassium dichromate. All right. That's one way to do a concentration example. right? The other way happens when uh, you're given the concentration and you're looking for some other quantity, right? You're solving for something else, okay? And in this case, we absolutely must use dimensional analysis to do this. I'm only gritting my teeth because I can't get my computer to do what I want to do. Okay. Gosh, thing is being picky today. All right. So when we're looking at this one, right, we have 632 milliliters of this solution of iron 3 chloride. Our answer is how many moles of chloride ions are in the sample. Okay, this is also a preview of something we're going to talk about later on when we talk about the stoichiometry of things in solution. So we're going to get kind of a twofer in here. I want us to remember that we have to use dimensional analysis to do this. And the way we're going to do this is our molarity is going to act as a conversion factor. So what we have is, I'm doing it again. I got to not do this. I'm sorry. 1.334 molar. Okay. This is FeCl3. This could mean 1.334 moles of FeCl3 in 1 liter of solution. Or it could mean that 1 liter of solution is 1.334 moles, okay? The one you choose, and I should label this as iron chloride, Cl3. The one you choose is going to depend on what your dimensional analysis tells you to do, okay? This also means I don't want you to start the calculation with molarity because there's a big chance you're going to get this upside down, and we don't want to get things upside down. Okay, so let's work through this pure dimensional analysis. So we're going to start with this 632 because this is the one unit. This is the one data we have that only has 1 unit with it. Okay, our concentration is in terms of liters, and this is milliliters, so we got to get our milliliters to liters, remembering there's 1,000 milliliters in 1 liter. Okay, once we have our liters, we can say that 1 liter of solution is 1.334 moles of iron 3 chloride. Okay. Now, if we stop here, this is going to give us moles of iron 3 chloride in the solution. Okay. You could go and get molar mass and look for grams if that's what we're looking for. Here, we're looking for moles of chloride ions. So moles of chloride ions, we're going to have to use the formula. So if we think about it, the computer's not behaving right now. If we have FeCl3, if we have 1 mole of this, there's a 3 here. And that means there's 3 chlorides for every 1 FeCl3. So this means we could say there are 3 moles of chloride in here, okay? And this sets us up for our next conversion factor, right? We're looking for, if we say 1 mole of FeCl3, okay, has 3 moles of chloride, okay? And then we figured it out. We got from milliliters of solution to moles of chloride. And there we go. This should be 2.529264 moles of chloride. And we want 3 significant figures. So really this is 2.53 moles of chloride. Notice in this one, we changed what the formulas were as we did the equation. So we had to put the formulas into our dimensional analysis. Okay. All right. Practice, practice, practice. Use your dimensional analysis. If you need me for anything, I'm here. Okay. Hang in there. We got this. I'll see you next time.